Welcome. We are going to do a quick review of the material we have covered so far and that will appear in our first exam. This is fall of 2017. We're going to look at, in this review, we're going to look at vectors, which is the first thing we have done, and then we're going to look at kinematics in one dimension. We have worked in kinematics in one dimension in several ways. We have done motion diagrams. We have also looked at graphs. And we actually work with algebraic equations in the case of constant acceleration. Algebraic solutions. Okay, let's start. Okay, we are going to look at vectors. So let me bring in an image with a set of vectors there. These set of vectors that you see in the screen, we have already developed some language to deal with them. First, remember that we have the following operations with vectors. We have the following operations, which are sum of vectors and a scalar multiplication. In addition to those, we actually, when we put these vectors in a grid, the way I have done here, we actually are able to do a few more things. We can talk about its magnitude, or the magnitude of a vector, magnitude, and also to talk about its direction with respect to the system of coordinates, direction. All right. So let us review that. First, let us review what it means to sum two vectors. So you have, for example, vector here A. I'm going to indicate it here. This is vector A. Note vector A there. And let's take vector C that is around here. That's vector C here. And if you want to sum two vectors, remember that what you do is that you take one A, and then you take the second one, and I'm going to move a copy of that here, and then you can actually construct the result by going from the beginning to the end. So this vector here then is A plus C. Very easy. Now, when we are provided with this Cartesian grid, we actually prefer to write the vectors explicitly in terms of unit vectors in the x and y direction. Remember that this is the vector right here. This is the vector I, and this is the vector j. So I and j. And then we can construct, for example, vector A. It is 4 units in the x direction, 3 units in the y direction, so we construct it as A is equal to 4i plus 3j. And we are taking advantage of the idea already of scalar multiplication. Remember that scalar multiplication simply means that we extend or make smaller our vector, or even flip it in the opposite direction. And this is indicated by simply giving the size by which we are changing the scalar. So for example, when I say 4i, I mean a vector that is 4 times in the same direction of I. Or if I say minus 3i, that means that I change the direction and make it 3 times larger. So that's easy. And therefore, we can construct this vector A as the sum of two vectors, one in the horizontal x direction, one in the vertical y direction. Now let us practice with summing vectors. So let us write again A. A is equal to 4i plus 3j. And C, the vector C, you can see here that it has 2 units in the horizontal direction. And we're going to write C is equal to minus 2i plus 4j. And then I can ask you, for example, to carry out the following operation. I can ask you to do the vector F is equal to 2a minus 3c. Again, this is a combination of vector addition, 2a plus minus 3c, and scalar multiplication, 2 times a minus 3 times c. And you can do this graphically, but it's easier to do it algebraically. So let us expand this, very simple, 2 times 4i plus 3j and minus 3 minus 2i plus 4j. And the net result, you just you just group together the i's, so you get 8 plus 6, that's 14. 14i. And in the j, you again group the j's, it's 6 and minus 12. So you get minus 6j. And then all types of combination of these. Occasionally I will, for example, add a variable here and then ask you to determine that variable. Or I ask you to solve an equation, but solving these equations is very easy. You simply use algebra. And the only thing you have to be careful is to remember that you cannot divide by vectors, but you will never need to do so. Another task that we need to carry out is to determine the magnitudes and directions of our vectors. For example, take this vector phi right here. So phi, we can write that as 3i plus 3j. And then what is the magnitude? Remember that the magnitude we represented by just repeating the symbol, but not marking it as a vector. Also, we can say absolute value or magnitude of that vector. And then we use the Pythagorean theorem because in the grid we can always create a triangle here. So with the right triangle with sides equals to the components along the horizontal and vertical direction. And then we just use the Pythagorean theorem to obtain this hypotenuse. So that means that this is the square root of the x component square, which is 3 square, and the vertical component square, that is also 3. So this is square root of 18, or 18 to the 1/2. So that's how we do magnitudes. The second task is to determine an angle with respect to the to one of the axes of in the system. So let's take the vector b right here, and then ask, for example, what is its what's the angle it makes with respect to the horizontal. And then we notice that the vector starts here, but then we are going to draw then a horizontal line here. And actually we complete this also again to a triangle. And then the angle is right here. So this is the angle alpha. And then we use trigonometry once more. And usually, because you are looking at a vector in the grid, you know what components it has. And if you know the components, these are the horizontal and vertical dimensions. Those are the sides of the triangle, and typically you solve this problem by calculating a tangent. So tangent of alpha is the opposite side, which in this case is the vertical component of the vector, 4 opposite divided by adjacent, which in this case is 3, and then alpha is the tangent inverse of 4/3. A slightly more complicated problem is when you actually need to express this vector, the direction of this vector with respect to not this angle, but for example, we can say with respect to the positive x-axis, what's the angle here? So then we have to construct these. We already determined the angle alpha here, but what we're looking for is all this angle. And then we simply say that this angle beta, from with respect to the positive x-axis, beta is 180 plus alpha, which is tangent inverse of 4/3. Let us now go to kinematics. The first thing we did to study kinematics is we restrict ourselves for a while to one dimension. So an object is simply going to be here in moving in this line. We are going to set a system of coordinates x. And then the motion diagram, it simply means that we put dots at the locations where your object is at a given time, and then we might see strange things happening or not. And then maybe it turns around and move them a little bit below so that you can see where it is going. So this is the motion diagram. In this diagram, we always are going to use a system of reference, and the times are going to be assumed to be equal between consecutive dots. So this is t equals 0, and this one doesn't have to be 1, but we can take 1, 2, 3, etc. Once we have this representation, we introduce the following concepts. We introduce the concept of position, which is simply to give x as a function of t. So the position, let's put some x in x. Maybe this is 10, 20, 30, 40, 50 or something like that. So, but we can say that x at x equals 10 at t equals 0. So that's just the variable x. Then we introduce the concept of displacement, which is delta x is equal to x final minus x initial for some process. So for example, from t equals 0 to t equals 1, our displacement is probably around 8, not quite 10. Remember that this is, in fact, this is the one-dimensional component of a vector, and therefore, when we describe it, we need to include its direction. And in one dimension, vectors are described by just one algebraic number, and that means that if my vector of displacement is this, it will have a positive, so we will say something like delta x is equal to 8. But when we go from this to this position, the vector of displacement is going to be, is a vector pointing left, and is represented by a negative number, so maybe minus 12. The next concept we introduce is that of velocity. V is equal to delta x over delta t, the displacement divided by the time interval. This is an average velocity for the process, and for simple processes we can actually compute it in this way. We are going to refine that in a moment. The hand, we have speed, which is the magnitude of the velocity. So that means that while the velocity can be a positive or a negative number, simply indicating whether it's moving to the right or to the left, the speed is always a positive number. We actually, a lot of times, we are going to add the superscript x to emphasize that this is a vector, and therefore we think of it along the x direction is going to be positive or negative, indicating that the vector points to the right or to the left. the vectors that we just described also need to be followed by one more. So we have position, displacement, velocity, and now we're going to introduce also the concept of acceleration. Acceleration is change in velocity divided by the time interval. All these quantities are vectors, and we can look at them in the diagram. And for example, a more complicated diagram will have we can point out at the displacements, and the vectors also look very similar, the vectors of velocity. So this is delta x. Let me add an arrow above the x to indicate a vector. And the velocity is going to be essentially the same vector up to a scale, because we're dividing by the time interval. But if we take the time interval to be 1, then essentially it's the same vector. How do you recognize positive or negative directions of the velocity? Very simple, it just points right or left. More complicated is the case of acceleration. So let us draw a diagram with an positive acceleration, which is the simplest case. So you have this object that is moving, and it's increasing its speed, its velocity, and therefore we obtain a vector with an positive acceleration. Those vectors of velocity are becoming larger. This has a positive acceleration and a positive velocity. But there are many other cases, and this is very non-intuitive. Remember that part. Let us draw a diagram with another positive acceleration, but where the velocity is negative. And what does that one look like? It's going to look like this. It's going to look as something actually slowing down. So we move this way, we move this way. So the velocity points to the left, but the acceleration as a vector points to the right, because at every moment we are modifying our vector of velocity in precisely this way. We are pushing it forward while the velocity is pointing left, pointing backwards. Therefore, the signs of the acceleration are non-trivial, and we discussed this extensively in lecture. We solved several exercises. Please be mindful of that. To solve problems associated with these motion diagrams, you simply have to read the diagrams, and it's easy to determine what are displacements, what are velocities. You simply take the displacement divided by time interval, and you can even estimate values of acceleration by looking at the velocity during some time before a process. So this is very constant velocity, and then you slow down, and then you stop. So before, you have some velocity that if you have a system of coordinates, you can determine, say it comes out to be 10, and during this interval of 2 seconds, you come to rest, and then it's easy to determine what the acceleration was. The average acceleration is going to be, if this is if 2 seconds elapsed, then the acceleration is going to be -5, because it is, let's do it here, AX is V final minus V initial in the X direction, divided by the time interval equals to, say, 0 minus 10 divided by 2 seconds equals to -5. The units are meters per second square, or whatever other units we might be using, but we generally are going to do meters per second square. Let's now look at graphs. So we have 3 graphs. We have the graph of position against time, So let me draw something here. We have a graph of velocity against time, and this graph of position against time just comes from observations, and the velocity versus time graph comes from the following observation. Turns out that if you have a straight line in the graph, then the slope of that graph, which is going to be the rise divided by the run, is equal to the velocity. So the velocity is the slope. And this is true even when we don't have a straight line. If we have a more complicated line, for example, like that, we can still take a limiting process and think just about very nearby points. We approximate that by a straight line, and visually it's easy to understand what the slope is, and then mathematically it requires a little bit more work, but it's clearly identifiable in practical problems, and therefore we simply say that the instantaneous velocity is the slope of the graph of position against time. If we do that process here, we obtain the following results. So we have first a constant positive value of the velocity because we have a positive slope. Then this region has zero slope, has a slope, but its value is zero. So you have zero velocity. We go back again to a positive value of the velocity, approximately constant, and then the velocity starts to change continuously. First it's here, it's close to zero, then it becomes negative and more negative. We go here and it looks like that. It's a strange graph. The acceleration is actually the same story, and acceleration is the same construction, is the slope of velocity. And the velocity, the acceleration here is zero because there's nothing. Then there's going to be quite a singular blip of acceleration there. We are not going to be very concerned about it. Then zero again. Then this again has slope zero. The interesting part is here. This graph has maybe it's close to a straight line, and you have an acceleration that is negative and approximately uniform. So the graph of acceleration looks like that. The second construction we're interested in graphs is the reverse process. So you have a velocity graph and with respect to time, and let us draw something here. And I want to know the displacement. So when the velocity is constant or uniform, like here, it's very easy because by the definition of velocity, you can only use this equation when the velocity is constant. If the velocity is not constant, then it doesn't, it is difficult to apply because this actually is a slope rather than a finite ratio of two intervals. So, but for constant velocities, you can apply this, and then delta x is equal to v delta t. And in this graph, if the velocity is constant, then we recognize this as an area. So delta x is equal to the area. The displacement is the area. A couple things to note: if your velocity is negative, then this area is negative. So negative area and negative displacement when you take a time interval in that region. And if you have a total process going from here up to here, then you have to add the positive and the negative contributions. But still the recipe is the same. Special cases. The special cases are that we work with are constant velocity, which is very easy. The more interesting is the constant acceleration. We described in lecture how to obtain these equations. Mainly, the first one, if you have a constant acceleration, you can simply rearrange this equation that you have, that delta v over delta t, and you obtain relationships of the following form: v final in the x direction is equal to v initial in the x direction plus the acceleration times delta t. So let me call this equation 1. And this is always true as long as your acceleration is constant. But in most processes, you're not going to have, or more complicated processes, you either don't have a constant acceleration, or it is constant but only for a limited amount of time, and then it changes to a different value. So be mindful of that. Otherwise, you cannot use this equation except in the cases where the time interval where the acceleration remains constant. But if you do that, we demonstrated in lecture that by calculating, by the process we just described a moment ago, the displacement given a velocity graph. So for constant acceleration, the velocity graph looks like a straight line. And then if you take that area for a given interval, it is, you obtain it by summing rectangle and a triangle, so you would get that delta x is equal to v initial delta t, vx, plus 1/2 of acceleration times delta t squared. So that's equation number 2. So the second term comes from the triangle, and the first term comes from the rectangle. Finally, equation number 3 is that if you can actually rearrange again this area calculation, changing the variable, instead of using delta t, use delta x, and delta v, and you obtain the final result as follows: v final x squared is equal to v initial x squared plus 2ax delta x, and that's equation number 3. Important application of the concept of constant acceleration. Turns out that we have a really important example, and that's free fall. Now, free fall actually does not mean that the object is falling. It's just that if you let it to its own devices, eventually it will fall. So you can throw something in the air vertically, throw it, so you give it an initial vertical velocity viy, and then the object keeps climbing, and it is actually this process actually has, when we leave the object to its own devices, it just experiences an interaction with the Earth, and the motion that results has a constant acceleration. The vector of acceleration points down, so that in a system of coordinates that points up, ay is always a negative number, and it is, we're going to call it minus g, where g is the free fall acceleration. And therefore we can we're able then to solve problems. We know what the acceleration is, and then we can apply the equations we just outlined. So let's give a quick example. We solved this problem in class. Let's take a look at it once more. So we are going to drop an object from a height h. I'm going to solve it algebraically. I'm not going to give a numerical value. So we drop the object from a height h, and we are going to observe it, and then we can ask, for example, if we know that height h, and at the beginning we just really drop it in the sense of just letting it go, not throwing it down, not throwing it up, with just letting it go. The we can ask, for example, what is the time it requires to it is needed for the object to fall all the way to the ground. Okay, so what we do is we usually collect that information, and we notice that this is going to be our initial condition, this is going to be our final condition. The initial condition then is as follows. Y initial is equal to h. The initial velocity is equal to 0 because I just let it go, and the moment it leaves my hand, it's not really, it was not moving, so it still continues to be 0 up to the moment it starts moving. And then the acceleration in the y direction, well, that's minus g. In the final condition, y final is 0. The final velocity we don't know, and by the way is not 0, because even though eventually it's going to stop because the ground is there, that's not the velocity with which it reaches the ground. So let's solve this problem. How do we solve it? So we take a look at the three equations we have, and we notice that that equation number 2 will be able to solve our problem because we know the acceleration, we know the displacement, and we then can solve for the delta t. So let's use that equation. So adapted to these circumstances, then we have the following equation. Delta y is equal to Vy initial delta t plus 1/2 of Ay delta t squared, running out of space there. So delta y is equal to 0 because there's no initial velocity, and the y acceleration is minus g, so I have minus 1/2 of g delta t squared. Let us solve this equation. So this is a quadratic equation, and then I just pass first all my non-delta t terms to the other side, and note the negative sign there, so I get minus twice delta y over g, and therefore delta t is equal to the square root of minus 2 delta y over g. This is my solution. Let us write it more nicely here. Delta t is the square root of minus 2 delta y over g. This is an example of a solution of a problem. Note that delta y is negative. Delta y is y final 0 minus y initial h, so it's minus h. So therefore, you're not going to have any problem here with the negative sign. So you're going to have 2h root square of 2h over g, and that is the way we solve those problems. Let us do one last example. So we are going to ask if we throw an object with a velocity v upwards, how long does it take to fall back down to the ground? Okay, so given v initial in the y direction, determine the time t in the air. So let's do that. So we look again at our equations, and this might look, this is not too hard. We can actually solve it in a couple different ways. We can use equation number 2 because we do know the initial velocity, we know what delta y is, It's just a quadratic equation. And then we also, well, actually, but that's what we are going to do. Also, we can use 1, but it requires a little bit of extra extra care. So let us do this. Let us do the fastest way, not the easiest, but the fastest way. The fastest way is to note that the process is symmetric. So let's do the symmetry of the system, because the velocity graph against time, T, V, starts at a positive value, goes through 0. It's a straight line. And the displacement, remember, is this area. So this is the height we reach. And then we have to come down. So we need to have the same height. So this area is h. And we want to come down to the ground. So this is going to be area minus h. By symmetry, because these two triangles have to have the same area and they are determined by the same line with a constant slope, then this time here is going to be t over 2 and this is going to be t over 2. So point is that going up it's going to take time t over 2 and down it's going to be time t over 2. Once you make that take note of that fact, then you can solve the problem very easily, because you can just determine how long does it take for me to get up there, and that's t over 2. And let us do that. So we use equation number 1 that says that by final is equal to by initial plus ay delta t. And so I want the time, that delta t is going to be t over 2. So let us write down everything in the way that we know. By final is equal 0 and the acceleration is minus g. So you have by final is 0 equals to by initial that we know minus g, and the time interval is going to be t over 2. So initial. So then the time is equal to 2 by initial over g. This is my time to go to the ground. Okay, that's the and there are a couple other ways to solve it, but we in problems that involve going up and down, it's very convenient to use the idea of symmetry. That is our review for the first segment of Physics 111. Remember that we have vectors, and you should know the key operations with vectors. You should know how to carry out sums and scalar multiplications, and you should also know how to calculate angles for those vectors, angles and magnitudes. Then you have to know how to interpret graphs of position against time, velocity against time, acceleration against time. The two basic rules are slopes and areas. You're going to connect them to motion diagrams. You should be able to interpret when you have positive or negative positions, velocities, displacements, accelerations. And finally, you have to know how to use the algebraic equations that we obtained for the case of constant acceleration. Thank you.